So any one of you is ready? You may go ahead.
Can I go first? Is that okay?
Of course.
Okay, thank you. All right. So my question was 6.40. It says in problem 6.3, calculate the conditional probability mass function of y1 given that x2 equals 1 and x2 equals 0. So this is my work. Somebody did 6.3 last class. Sorry, I wrote 3.6. I was doing it fast, but so I just made a little chart to help me see it easily. So the first one was to find when y2 equals 1. So that means y1 could equal 1 or 0, so I split it up into two parts. So first, given that if y1 is 1, given that y2 is 1, so I made the probability formula, and then I made it into probability if it's 1, 1 over 0, 1 or 1, 1, since those are the choices. And then I took from the chart. So it was 1 over 26 divided by 5 divided by 26 plus the 1 over 26. And then I did that again, but if y1 was 0, because there's two possible scenarios. And then I realized I could have done it differently, but I'll say how I did it this way. Was I made it into the probability that y1 is 0 given y2 is 1. And then I would do the probability if it's 0, 1 over the probability if it's 0, 1 plus probability if it's 1, 1. However, I probably didn't have to do all that work because I could have done 1 minus the 1, 6, but it was still good practice, so it's okay. And then the next one was if y2 was 0, you also have two opportunities. So you either get y1 is 1 or y1 is 0. So I plugged in that probability is 1, 0 over 1, 0, 0, 0 because that's two options. And then taking from the chart, it was 5 over 26 over 5 over 26 plus 15 over 26, which gave 1/4. And then I kept doing more work that I probably didn't have to do again. And I did the probability if y1 is 0, given that y2 is 0, since this one also exists. So 0, 0 over the probability of 1, 0 plus the probability of 0, 0. And that gave me 3/4, even though I could have done 1 minus 1/4 equals 3/4 also.
Yeah, but that's okay.
Yeah, just more practice.
Yeah. Okay, nice. Thank you.
Thank you.
Hi, Professor.
Hello, Catherine.
Okay, so I'm presenting 6.37. An experiment is successful with probability 0.8. A, what is the probability that 2 runs of the experiment yield no success? And B, what is the probability that 10 runs of the experiment yield higher than average success? So for this question, it deals with binomial distribution. And so we know that probability big X equals to small x equals to n choose x times p to the x power times q n minus x power. And we know that for the success, we have 0.8. And for probability that is not success is q equal to 1 minus p. So the probability that is not success is 0.2. So for part A, what's the probability that 2 runs of the experiment yield no success? So since we know, so we just plug this into our binomial distribution of probability that x equals to, I think there's supposed to be 2 there. Was it?
No, 0, no success.
Yeah. 2 choose,
right.
Yeah. 2 choose no success. So 2 choose 0 times 0.8 to the 0 power times 0.2 times to the 2 power, which give us the 0.4 probability that 2 runs of experiment yield no success. And for part B, but just 10 runs.
Hold
on.
No, it's 0.04, right?
0.4, I think.
0.2 squared, 0.04.
Oh. I probably wrote it a bit wrong, but
yeah, you said missing 1 0.
Yeah, sorry about that.
0.04. That's okay.
Sorry.
Okay.
So we have the next one is 10 runs. So we just for this one we need to find our average success, which is n times p. So we have 10 runs times successful probability 0.8, which equals to our mean, that's 8. And to find a higher than average success, that 10 runs of experiment, so it's probability that x is greater than 8 equals to probability that x is equal to 9 plus probability that x is equal to 10. So, and then this part we use binomial distribution. 10 choose 9 times 0.8 to the 9th power times 0.2 to the 1st power plus 10 choose 10 times 0.8 to the 10th power and times 0.2 to the 0th power, which give us the probability that is 0.3758.
Okay. Nice. Nice, Catherine. Thank you. Okay, who's next? The boys now.
Can you see my screen?
Yes.
This is 6.33. The x1 and x2 will be the sum of 10,000 Bernoulli trials, with the probability of a successful outcome being 1/2. Use the normal approximation to the binomial to determine which probability is larger. So for the part A, we're comparing those two, and since it's Bernoulli, we gotta use continuity correction. So we can use it. So after continuity correction, we can use normal distribution. So for x less than 5,000, after the continuity correction, we got x1 less than 4999.5, and we just do the calculation and use this chart.
Converting to z-score, right? Converting to standard normal variable z-score.
I'm sorry?
It's called a z-score. Let me type in the chat. So when you convert from x variable x to z, it's called z-score. I don't know why they call this name. Basically, you change a normal distribution to a standard normal distribution. So you have the 0 as a mean, then first deviation from -1 to 1, then second deviation from -2 to 2, then -3 to 3, then the outskirts, like that. So it's called a z-score.
So z-score.
Yeah.
So for the left-hand side, we got this. For the right-hand side, since the probability of success is 1/2, the component is also 1/2. So the mu and the sigma of x1 and x2 will be the same. So the average will also be the same. So we use continuity correction, and then we calculate it and then we found this, because we cannot find this number exactly, but we know this number is between 0.00 and 0.01. So we know this the probability for this would be between 4960 and 5,000, which is bigger than 4960. So for the part A, this would be bigger. And
hold on one second. So this is convolution. So I forgot the formula. The formula is just you can convert directly into z-score for x1 plus x2.
for you mean?
This is convolution. Yeah.
So usually we gotta figure out the mu and the sigma for x1 and x2, and then we find the average of them. Then we use it to calculate it. But in this case, the mu and the sigma of both of them are the same, so the average will also be the same.
Oh, okay. I see. I got it. Thank you.
And for part B, similarly, we gotta use continuity correction, and we do calculation. And similarly, but once we find this, we cannot convert it because the largest number is 3.49, but we know it's bigger than 0.998. So the
It's
component of
outliers. We call outliers. Okay.
and so the component would be less than 0.0002 compared to the left-hand side. The left-hand side would be bigger.
I see. Nice. Nice. Okay. Thank you, Jen. Oh, you have 200. Would we have to have these types of questions on final? We will need a chart or the normal distribution, the standard normal distribution. You're right. We'll see. We'll see. Not to worry about the final yet. Next one.
I got question 31. According
Okay.
to U.S. National Center of Health Statistics, 25.2% of males and 23.6% of females never eat breakfast. Suppose that random sample of 200 men and 200 women are chosen. Approximate the probability that at least 110 of these 400 people never eat breakfast. B, the number of women who never eat breakfast is at least as larger as the number of the men who never eats breakfast. By the giving numbers, the percentage of men and women and the simple space is given, I calculate the expectation, which X for men, Y for women, and then variance to get sigma. Then for A, we want at least 110 of out of 400. So I add up the expectations of men and women, and then also find the sigma for the men and women. Then applying the z-score formulas of 8 greater than or equal to 110, then plug in the numbers to get z-score is greater than or equal to 1.385, and then you subtract the z-scores to get 0.0829. That's at least 110 of out of 400 people never eat breakfast. And then for B, it's probability of Y woman greater than or equal to man X. It's the same as this Y minus X greater than or equal to 0. Then which I find the expectation of Y minus X to get next 3.2 and sigma as 8.59. Then continue plugging into the formulas to get 0.3766.
Okay. I have a question to ask. Can you go to the top? What kind of distribution is this? Oops. Okay, basically my question is, how do you know the expected value is a linear relation? Basically just add up those two. I'm curious about that.
It's like it says here is 400, so it's like simple space of 200 and 200 to that up. It's like valve here. It's
No.
like you mean this one?
No, I just mean the expected value. You see, you have E of x plus y. Yeah, this one.
Oh,
so
this
E
one,
of,
it's like, because it's like 200 men and 200 women. One's like 400 people out of it.
Okay, so my question is, expected value, the convolution, I don't know. So expected value of x plus y is E of x plus E of y.
Yeah.
I see. Then the variance is the same thing, is adding those two?
Yeah. Because like it's like,
so adding
like,
adding the two squares and then square root. Okay, I don't remember
variance of like x plus y, and then it's variance of x plus variance of y.
Then square
and then
root.
Square root.
Okay, got it. Thank you. I don't remember this. Okay. All right. Catherine wants to see B again.
B? Okay.
Yeah. Yeah, B basically is similar. So if you know how to calculate the expected value and the variance. Okay, thank you, Hal. Nice.
Hi.
Hello, Angeli.
I'm doing 6.29. It says the total rainwater collected in a reservoir in a year is gamma distributed with mean 1,000 liters and standard deviation 200. Assuming that the rainwater collected yearly is independent, what is the probability that A, the total rainwater collected by the reservoir in 2 years is less than 2,500 liters, and B, more than average collection of rainwater happens in at least 3 of the next 5 years. So total rainwater collected in a year X has gamma distribution, and the expected value is 1,000 liters, and the variance is 200 squared. I solved to find the scale of 40 and shape of 25. Question A says the total rainwater collected is less than 2,500 in 2 years. So the gamma distribution would be, the shape would be 50 for the 2 years, 25 by 2, and the scale would be 40. And in the gamma distribution calculator, I got 0.9540.
Just use calculator. Okay.
Yeah. Seeing that the mean is 1,000 a year, then it's a 95% chance of less than 2,500 for 2 years.
Wow, that's high.
Yeah. And then B, it says more than average collection of rainwater happens in at least 3 of the next 5 years. So same thing I used, but 1,000 every year.
The average. 1,000.
Yeah. And I got 0.4734 again in the calculator. And using binomial distribution, I got 0.45.
Okay, nice.
So it's a 45% chance of getting
In the next 5.
3 of the next 5,
Next.
and then it's high. 95% is high because the mean is 1,000, so 2 years would be around 2,000. So it's a high chance to get less than 2,500.
Okay. Very nice. Thank you. That's Andrevi.
Hello, Professor. Good evening.
Hello, good evening.
I'm going next, Professor.
Okay.
When you will see my screen, can you let me know?
Okay. Not yet. Oh, Catherine, the second one is about 45%.
Yes, Professor. Can you see
Yeah, I
my
didn't
screen?
see it. I just heard it from him. Yes, yes, Ikera.
Okay. I'm going to present 6.30. A manufacturing plant uses 2 machines in 2 stages. The service time in minutes of the first machine is normally distributed with mean 1, and standard deviation is 0.05. Independent of the first machine, the service time of the second machine is normally distributed with mean 0.95 and standard deviation is 0.02. Find the probability that the first machine finishes the task faster than the second machine, and B part is the total service time for the both machines is less than 2.1. Let x be the service time of the first machine, mu x is equal to 1 and sigma x is equal to 0.05, and let y be the service time of the second machine. So mu y is equal to 0.95 and sigma y is equal to 0.02. The probability that first machine finished the task faster than the second machine, probability x greater than y, is equal to probability into x minus y greater than 0. So let t is equal to x minus y, and expected value of t is equal to 1 minus 0.95, which is equal to 0.05, and variance of t is equal to 0.05 raised to the power 2 plus 0.02 raised to the power 2, which is equal to 0.0029. And here z is equal to t minus expected value of t over under root variance of t, which is approximately equal to n into 0 and 1. P probability into x greater than y is equal to probability t greater than 0. So probability z greater than 0 minus 0.05 over under root 0.0029. After taking the under root, we will get the value 0.0538, and it will be the value in negative 0.93. So probability x greater than y is equal to, we will find a complement, which will be equal to 1 minus probability into z less than equal to 0.93. Probability x greater than y is equal to 1 minus 0.0230. By using standard normal table, we will find this value, and our after subtract, we will get the value 0.1762. This is the answer of the first part. And for the B part, the probability that the total service time for both machines is less than 2.1. So U is equal to X plus Y total line. So expected value of U, which will be equal to 1.95, and variance of U is equal to 0.0029, and Z is equal to U minus expected value of U over under root variance of U, which will similarly with the part 1, it will be n into 0 and 1. And probability u less than 2.1, we have to find this one. So it will be equal to probability into z less than 2.1 minus 1.95 over under root 0.0029. So after solving it, we will get that z less than 2.70, and when we will get the value from the table, so it will be the 0.9973.
Wow, almost 100%.
Yes, Professor.
Okay, thank you, Ikera. Nice.
Thank you.
Thank you. Tom. Okay, Tom. Let me make a presenter. Ayat, sure, Ayat. All right. Who's ready? All right, thumbs up.
Hi, can you hear me?
Yes.
Okay. So we have the joint probability density function of x and y is given by this constant 4ln 2 squared times 2 to the minus x plus y. So I just substitute c for that constant part of 4ln 2 squared times 2, which is about 2.843. So just substitute c, so I don't have to keep writing that. Anyway,
Hold on. Why you multiply by 2? You don't have 2. You do have 4. You have ln 2 squared.
Isn't there's a 2 on the right side?
The 2 is a base of negative x plus y. That's not a constant. That's not part of. Right.
Oh.
Divided by 2.
That whole thing is raised to the minus x plus y, isn't it? Or is it
no,
just...
but 2 itself you cannot calculate as a constant because 2 is a base of negative x plus y. You want to calculate the scalar, right? The scalar is only 4 and ln 2 squared.
Okay, I see. So I guess the calculation will be slightly off then. Yeah. All right. Well, anyway,
let me see. Oh yeah, use it divided by 2. We can take a 1.92. Yeah, just divide your 3.843. Use it divided by 2. Because I just calculated for you. It's a 1.9218. Okay. Yeah. Keep going.
Okay, so we're finding.
Okay, Tom. Okay, Tom, hold on. I know. I see what mistake you have made. You want to make now. You have this. Okay, let me make this one. That's very interesting. Now you want to see that's a c raised by negative x plus y. No. Okay. This is called scalar. This is a number. This is a c. Yeah. But your base is forever 2 raised by negative x plus y. Okay, so you have c multiplied by 2 raised by that. Then your c is just you multiply this by 2. Oops. 1.92 something. It doesn't allow me to write it. Yeah, just take this one. So you have 1.921 something multiplied by 2 raised by negative x plus y. Okay, keep going.
Okay. So we have to find probability x less than a. So we take the integral from a to 0 of of fx dx. Fx is equal to the integral 1 to 0 of the joint distribution with respect to y, and then gotta use the calculator for that part. So I got c minus 1 to the c to the minus x minus 1 over log c, and then once we find fx, we plug that in to the integral from a to 0, and then the part in red is what I got, and find the probability x plus y is less than 1/2. So I got the area under x plus y is less than 1/2 from x is from 0 to 1/2 and y is from 0 to 1/2. So we got 1/8 for the area there. Then I multiplied that by fxy, which was given here. Yeah.
Okay. Yes. All right. Thank you, Tom. Okay. Ayat, are you ready? Oh, you have the same one?
Yes, I have the same questions present. Okay, so maybe next time, right?
Oh, well, can you choose another one? You don't have anyone else?
No, I prepared this one. It's a long one.
It's exactly the same as, well,
No,
go ahead.
It looks different. It looks different, yeah.
Looks different, right? Look different, go ahead.
Mm-hmm.
Yeah.
Okay. All right, so that's the question. So it's right. In part A. So probability of x less than a. I use this function, put the function in double integration, and separated this integrals by dy dx, dy from 0 to 1, dx from 0 to a. Then I separately integrated dx, and I got this one, 1 minus 2 to the power minus a divided by logarithm 2, ln 2. Okay, so use this result and put this into the beginning formula, and then I integrated by dy. In integral from 0 to 1 by dy is 1 over 2 multiplied by ln 2, and I got this result. By simplification, I got 2 to the power a plus 1 minus 2 over 2 to the a, and that's the answer in the text in the book. Okay, so and for part B, probability of x plus y less than 1/2 is the same as probability of x less than 1/2 minus y. Okay, so integration is the same as in part A, but the their y integration is from 0 to 1/2, and the dx integration is from 0 to 1/2 minus pi. Okay, so that's similar to the calculation in the part A, and the result was 0.19.
I'm sorry, I was talking. I mute myself. Why? Right. My question is why? Why this integral y goes from 0 to half? This one.
That's because x plus y is less than half. That means y is cannot be more than half.
That's right, because x, because the lower bound of x is 0, it's not a negative number. Okay, great, very good. So yours and Tom did, like divide and conquer. So you did everything together. But the only thing is Tom calculated C, not 100% right. Okay, so that's Ayat. Let me give you credits, so I won't forget. Oh, yeah, you reached 100%. All right, anyone else like to present today? If not, you can prepare next class. So let's see, today we're going to talk about exchanging random variables. I'm just taking the pic to see what's involved. That's it. Hold on, has nothing to do with exchanging variables. Maybe I didn't choose it right. Exchanging random variables. Oh, maybe here. Remember in vector calculus, very important concept is to exchanging variables. Then we have the Jacobi. Remember this guy, our old friend, Jacobi. Okay, I guess it's this, joint probability distribution of functions of random variables. I'm not sure, let me check our syllabus. I remember it's exchanging variables. Okay, convolution, we call functions of random variables. Change of variables formula. Joint probability distribution of function of random variables. Okay, it is this one. Yeah, I just have allergy. I'm not sick actually. I just have allergy from time to time. I just sneeze, but it's okay. I'm pretty healthy. Okay, let's see this one because I like this topic. So this is functions of random variables. Oh no, what did I do? Because this one we can apply old stuff. Did Did I do more? Did I do less? Oh, here. Okay, let's read. Let x1, x2 be jointly continuous random variables with joint probability density functions of f of x1, f of x2. Oh no, f of x1, comma x2. It's sometimes necessary to obtain the joint distribution of the random variables y1 and y2, which arise as functions of x1 and x2. Specifically, suppose that y1 equals to g1 takes x1, x2 as variable, y2 equals to g2, a function of x1, x2 for some functions of g1, g2. So you see the similarity with when we talk about vector calculus, right? Assume that, so basically we form a plane of x1, x2 to the plane y1, y2. You could think that way. Assume that the functions g1, g2 satisfy the following condition. Okay, so we do have some conditions to know. First, the equations y1 is a function of x1, x2, y2 is a function of x1, x2, can be uniquely solved for x1, x2. Yeah, the uniqueness is always required. In terms of y1 and y2, this is very similar to vector calculus with solutions given by saying x1 can be represented as a function of, in terms of y1, y2. x2 can be represented as a function of y1, y2. Okay, so the uniqueness we can find, we can go from one plane to another plane, right? So basically, you could think this doesn't have to be one-on-one, one-to-one relationship, but basically you have this kind of inverse. You can go from x1, x2 plane to y1, y2 plane, and from y1, y2 plane to x1, x2 plane. The second condition is the functions g1, g2 have continuous partial derivatives, of course, right? Otherwise, we won't be able to calculate Jacobian. And so have this. This is all older stuff. Hopefully we all remember this, right? The partial derivatives. So with these two conditions, so we have this. We have a density function, joint density function for y variables, and equals to the joint density of x variables, but with a scalar of the Jacobian. With a scalar of Jacobian. Okay. If you want to see the proof, go ahead. Excuse me. Let's see some examples. x1, x2 are joint continuous random variables with a probability density function represented this way, fx1, comma, x2. So let y1 be the sum of x1, x2, y2 be x1 minus x2. Does this remind us the first very example in vector calculus when we talk about exchanging variables? It's a linear change, so linear transformation. You could think this is a linear transformation. Find the joint density function of y1 and y2 in terms of this. So basically, we think as, okay. So G1, call this G1, call the minus is G2. Then the Jacobi is just this partial G1 x1, partial G1 x2, partial G2 x1, partial G2 x2, right? So calculate, we'll have -2. So the Jacobi is -2. Now, since the y1 is the sum of those two, y2 is the difference of those two, then we can, because we have these two equations, right? We put together the system, a system of two equations. So we can solve for x1 in terms of y1, y2, and x2 in terms of y1, y2. Especially the linear relations is easy to do this. Then, so we use the formula of 7.1. So Fy1 is density, joint density function for y1, y2 is just the joint density for x1, x2 multiplied by the inverse of the Jacobi, because in the formula, it's the absolute value of the inverse. Okay, absolute value of the inverse, multiplicative inverse. So that's why we have, so the inverse of absolute value of -2 is just half. So if, for an example, if x1, x2 are independent uniform random variables, then this one would be okay, right? Or if x1, x2 are independent exponential random variable with number 1, number 2, then this one would be right. So if it's a standard normal, which is putting in the standard normal, so get this one probably easier, right? So this can be used in examples. Let's see. So this example, let xy denote a random point in the plane and assume that the rectangular coordinates x and y are independent standard normal random variables. We are interested in the joint distribution of r radius and theta, the angle, I guess. Oh yes, the polar coordinates representation of x and y. And we know x equals r cosine theta, y equals to r sine theta, right? That's the polar coordinates with the rectangular plane. Suppose that x and y are both positive, x and y, letting r equals to the radius. So consider r as g1 of xy, square root of x squared plus y squared, and theta is g2, which is the arctangent of y over x. So basically, this is just assume everything in the first quadrant. So we see that partial g1, partial x, right, is this. Partial g1, partial y is this. Partial g2, partial x is this. Partial g2, partial y is this. So Jacobi, if we calculate, we get 1 over r. Interesting, huh? Remember when we calculated the area from, if we have integral, double integral from the plane to the, what do you call it, polar coordinates, the Jacobi is r, right? The Jacobi is r. But here, with this one, what do we do? So g1 is this. So g1 is a function in terms of x, y. g2 is a function, though of course g2 is a function in terms of x and y. So from what do you call it? R theta from the polar coordinates to the rectangular one, the Jacobi is 1 over r. Right? Same as before, nothing changed so far. Let's see this. Conditional joint density function of x, y, given that they are both positive. Okay, so we see that, so this is both positive. So we just consider in the first quadrant. And so we have this density function of f, x, y, and with both positive. Okay. So we see that the conditional joint density function of this and that given x and y is this fr theta in the first quadrant, right? 2 over pi r e to the negative r squared over 2. Right? R is this defined this way, square root of x squared plus y squared. Similarly, we can see that So y is positive, x is negative. So that's in the second quadrant. In the second quadrant, we have the same thing. In the third quadrant, we have the same thing. Right? Okay, in the four quadrants, we all have the same thing. So we can define this. So we have this. Theta runs from 0 to 2 pi, and R runs, R is positive. So we have this. We have this f of r theta equals 1 over 2 pi, r e to the negative r squared over 2. And yeah. So that's the relation between xy plane and r theta plane. So the joint density function in the polar coordinates is this. Now this joint density factors into a margin density with theta being uniformly distributed over 0 to 2 pi, having the Rayleigh distribution with density of this. All right, that's something more than we need to know. Okay, let's see this. If we want a distribution of r squared and theta, then since the transformation G1, so no more square root, but the theta is still arctangent. Then we calculate, we have the Jacobi equal to 2. Then in this case, remember this is r squared, right? So something like this. Let's see this example. If x and y are independent gamma random variables with parameter alpha lambda and beta lambda respectively, compute the joint density of x plus y. U equals x plus y, v equals x divided by x plus y. Okay, this transformation is not linear. Let's see this. The joint density of x and y is given by yeah, we calculated this last class, right? We have seen this. Now, if G1 is x plus y, G2 is x divided by x plus y, then we can calculate partial G1, partial x is 1, partial G1, partial y is also 1, partial G2, partial x is y over this, partial G2, partial y is this. Then we calculate the Jacobi, which is negative 1 over x plus y. Then from these two equations, we can solve for x and y in terms of u and v. X will be u times v, y will be u times 1 minus v. So the uv plane density, the joint density function on uv plane will be fxy, the joint density function on xy. But take the variables of x is uv, y is u times 1 minus v, right? Take this one, then u. Okay, if we substitute into this, so x is uv, y is u times 1 minus v, so just plug in. Very complicated, very cumbersome representation. So this basically is saying, okay, x plus y, u and v are independent. Then x plus y having a gamma distribution with parameters alpha plus beta gamma. And this having a beta distribution with parameter alpha and beta. So this is saying the preceding, so normalizing factor is such that B, that's okay, we don't have to know this. When the joint density takes n variables, you know, of course we can calculate the Jacobi, right? The determinant is defined on 2 by 2 matrix, but we know how to do higher. As long as it's a square matrix, we can always calculate the Jacobi. We can always calculate determinant. And the same thing, we can always calculate Jacobi determinant. Let's see this example. So we have x1, x2, x3, independent standard normal random variables. So let y1 be sum of those three, y2 be x1 minus x2, y3 be x1 minus x3. Compute the joint density function of y1, y2, y3. Yeah, this is a more, yeah. So we can calculate the Jacobi, right? Partial y1, partial x1, 1, partial y1, partial x2, 1, partial y1, partial x3, 1, partial y2, partial x1 is 1, partial y2, partial x2 is negative 1, partial y2, partial x3 is 0, partial y3, partial x1 is 1, partial y3, partial x2 is 0, partial y3, partial x3 is negative 1. So the Jacobi equals 3. And then we need to represent it. So we have 3 equations, right? And we can represent each x, x1, x2, x3 in y1, y2, y3. So we did that. x1 equals to 1/3 of the sum of these 3. x2 equals this. x3 equals this. So we just rewrite. So we just write the joint density function as this. So it's 1/3, 1 over the Jacobi. Then f joint density function for x with these new variables, right? So this is changing of variables. That's how we change the variables. Since this one is this, so f with y's, right? Just calculate that. And representing this one with the combo sum expression. Anyone has any question? This is a good example. Let's see the next example. We have n independent variables, identically distributed exponential random ones, with each with lambda, with lambda. So yi is x1 add up to xi. And I, of course, goes from 1 up to n because we have n variables. Find the joint density function of y1 up to yn. Then use A to find the density function of yn. Then find the conditional density of y1 up to yn minus 1, given that yn is some number. Okay, so we calculate Jacobi first. y1 will be x1, y2 will be x1 plus x2, y3 will be sum of 3 variables so far, yn will be x1 adds up to xn. So we calculate it, we have this matrix. Then we calculate the Jacobi. The Jacobi is, so we just go down the ladder, right? 1, stuff like that. So in the end, the Jacobi is just 1, right? This is like a triangle matrix. Jacobi just 1. Now the joint density function. So for x is this is for x equals the product of the lambda times e to the negative lambda xi, and then multiply n of them, right? Xi goes from x1 up to xn. Then if we want to solve for x in terms of y's, we have this, where x1 equals to y1, x2 equals to y2 minus y1, xi equals to yi minus yi minus 1 up to y1, and xn equals to yn minus yn minus 1. That's the last one. Okay. So it follows that the joint density function on y's is the same as joint density on x with these new variables, right? New variables represented by y. B, the margin density of yn. So let's integrate out the other variables one at a time. So let's see. Okay, so f of this is with y1, right? Then we just get this, and y3 up to n. So this is y2 up to yn, I3 up to yn will be, what's the difference? You see, only this term is different, right? Only this term. So next one is same thing. We have this. The variable raised by 3 for the, so this is number third. Y raised by square divided by 2. Number fourth raised by 3 divided by 3 factorial. So we can make a general case. That's nth y raised by n minus 1 divided by n minus 1 factorial. So which in agreement with the result in example 3b shows that x1 adds up to xn is a gamma distribution. Let's see C. The conditional density given that yn equals t, right? With all this, only the nth term is t. Excuse me. So that's lambda raised by n e to the negative lambda t, right? Lambda raised by n. So that means this one just equals to 1. Yeah, because 1 minus 1 is 0, right? Y raised by 0, that's just 1. So take this. Then the denominator is fynt, which is this guy, just with yn to be t, which is this. Then simplify a little bit. So this will have lambda n minus 1 and lambda, that's lambda n, so cancel with the numerator 1. Then e to negative lambda t, we have this one here, cancel out with each other. And what's left? We have t raised by n minus 1, right? But then this term goes to the numerator. So I have n minus 1 factorial divided by t to the power of n minus 1. Isn't it nice? Okay, this is a good example. And because the density on y equals 1 over t is the density of a uniform random variable on 0 to t, it follows a conditional on yn equals t, and y1 up to yn minus 1 distributed as the order statistics of n minus 1 independent uniform random variables. All right, so that's it. So what's important for us is the Jacobi, is we know, these kind of examples. All right, pick some of this kind of homework to do it. Calculate the Jacobi, then just use 7.1. Okay, so for us today, just this. All right, just this. So this is changing variables. All right, changing variables from one plane to another plane. We calculate the Jacobi. Then they just scaled. They're equal to each other with a scalar. That's it. All right. Anyone has any questions? If no questions, you are free bird. You can go ahead, start your homework. If you do have questions, I'm here.